All right, good morning, everyone. Welcome to SMUD's virtual classroom. My name is Megan Cordes from SMUD's Community Education and Technology Center. We hope you're staying safe and glad you've joined us for this presentation. On behalf of SMUD, welcome to the why and how of home performance for electrification. This will be recorded. SMUD is a not-for-profit utility owned by you, our ratepayers, and because we're community-owned, we're focused on our customers. That is one of the reasons why we offer a variety of educational and online resources. This workshop supports SMUD's new clean energy vision to have carbon-free energy production by 2030. All of our workshops are being recorded, so please check them out at smud.org/workshops. Before we get into the webinar, I'd like to update you on some programs that we have available for you and your customers. These are just a sampling of our programs. We have lots more, so if you have any questions or would like to know more information, please reach out to us as early as possible. SMUD's electrification program highly encourages our customer base to electrify the grid with heat pump technologies, which are more efficient than gas or electric resistance for space heating and domestic hot water heating. We have a custom retrofit program and an integrated design solutions program. Both of these, in addition to design assistance, offer incentives up to $150,000 for beneficial electrification and up to $10,000 for energy efficiency. In addition, they offer up to $10,000 design team incentives for all electric designs that shift gas usage to electricity. SMUD's Power Direct program is an auto demand response program that offers incentives for setting up the equipment as well as ongoing participation with electrical load shedding. SMUD's Green Energy program offers renewable electricity from off-site, allowing customers the benefits of operating off renewable electricity without maintaining systems on site. And Energy Solutions is a commercial rebate program geared for retrofit applications of smaller system types. So after this presentation, you'll receive a couple of emails from us. The first will be a short survey. I'd love to hear your feedback as always. I definitely want to address any questions that you have, fill any gaps in knowledge that you'd like to see. So please let me know what you think. The second will be a downloadable certificate of attendance. If it's okay with you, Larry and Alex, I'd like to also send a PDF of the presentation. So yeah, okay, thanks. So we'll send that out afterward as well. During the webinar, you'll be muted, but you can ask questions via the chat area on the side of your screen. I will try to monitor the chat. We'll answer any questions that we can during the webinar. Anything we don't get to, we'll save for the end. So with that, I'd like to introduce our speaker, Larry Waters. Thanks again for being here. We're happy to have you back, and go ahead and take it from here. Thank you.
All right. Good morning, everyone. Hey, thank you for taking time out of your lives to learn a little bit more about good electrification. So today we're going to talk about the why and how of home performance for electrification. Just my bona fides, so you know that I've been doing this a minute. I've been in the HVAC trade since 1982. I actually was in the trade before the first cordless drill. I remember when these started being available. It was a game changer. Lots of game changers since then. NATE certified for over 20 years, BPI certified, Building Performance Institute certified in 2010, and I've maintained both of those certifications throughout the years. I have only been installing heat pumps since 2015, and I founded this company, Electrify My Home, in 2020, mostly because somebody had to do it. Our mission, we're a very mission-driven organization. We do everything a little different here at our company. This isn't about that, but just our mission, excuse me, to provide the most efficient, cost-effective electrification solutions, be a good steward of the electrical panel. And what I mean by that is we make recommendations that are going to use the least amount of breaker space and least amount of power possible to electrify someone's home, and then train and influence other contractors to do the same. This small piece of this 1.5 hour webinar today is just part of what we teach on in our Tech Clean California program that will be coming up to this area in the fall. So if you're interested, that's a fun 3-day class where you just get a complete immersion. So we're going to give you a little bit of intro to home performance electrification basics, some of the unintended consequences of just box swapping with a heat pump, why it's super important to know what size system you need, and how far do you need to go with home performance, it's different in every example. And then we're going to give you a project example in the end, and do closing and wrap up with some questions. So if you have any questions during this, you can put them into the chat. Alex, who is on the line with us as well, will try to answer those, but then we'll go over all of them at the end. Please think about whatever questions you have, and let's get those out there. All right. So what is home performance? I'm sure a lot of you on this call are probably pretty dialed in and understand what home performance is, but home performance is looking at the house as a system. It describes how all aspects of the house work together as a single system: insulation, plumbing, air sealing, designing systems for the right size, and doing measures in the house that makes the effective capacity of the house smaller so we can put in more efficient systems. It's a science-backed approach based on the premise that houses need to be safe, healthy, super comfortable if you do these right, durable, efficient, and the one we add is quiet. Our systems are mostly inaudible. You can't really hear them inside the house because they're well balanced and they have enough, they have low static pressure. Our motto of the day is the best outcomes for heat pumps come when multiple elements of the home are considered. And it's really not that hard to do. We just need to think beyond the box. So we're going to go into some of the basic stuff, like, I'm sure if I could see hands raised, but I'm going to ask just the question. Who knows the basic laws of thermodynamics? Like, they teach us all of this in technical school. If we go there, we went to college, or however we learn this stuff, it's really a principal effect and a principal need to understand this, especially with heat pumps and proper sizing of systems. We want to remember pressure differentials. Pressure is always going to move from high to low. Heat is always going to move from warm to cold. Moisture is always going to flow from the big puddle to the little puddle. Energy is going to be, you put energy in, it's going to equal energy out. And if you have an air leak, if it leaks out 1 CFM on that side of the house, that 1 CFM is coming in from the other side of the house. So these are the important ones that we need to know as part of our design and understanding of how these systems work. Three critical elements of the building enclosure. So this is like home performance 101 here. We need to understand these things and how they operate and influence each other in order to understand how the system is going to work. And first we have the air barrier, the pressure boundary, and the thermal boundary. Let's talk about the air barrier. So the air barrier is the area inside your room. If you're looking around, it's the inside of the door, it's the inside of the windows, it's the inside of the ceiling and the floors and the walls. It's anything that's going to keep that air. It should be impenetrable to airflow. It should be continuous over the entire building enclosure, able to withstand the forces like wind and rain, obviously durable, and define the location of the pressure boundary. And you can see in this little diagram here that this air barrier that exists inside here, we need to keep the air from other areas out. And we need, in order for us to have an effective pressure boundary and thermal boundary, we need to make sure that these are all aligned. The pressure boundary. So the pressure boundary is the area that exists between the two outside areas. If you have a single story house and it has an attic that's separate and a crawl space that's separate, the pressure boundary is the ceiling and the floor. That's what's keeping the pressure differential between those two spaces. When we have a break in the pressure boundary, it can cause all kinds of problems. And so houses with crawl spaces typically have this problem. So the one of the things that needs to be considered is when you're doing this is looking at how these pressure boundaries react. And if you're doing things like blower door testing, these are easy to find. But if you're crawling underneath the house and you see a big hole underneath the bathtub, or you're seeing in a 2-story house, you have the chase that goes down where the ductwork is coming up from the garage, and you have the interstitial wall cavity, that's a pressure boundary break because it's going to connect with the middle floor. So the pressure boundary is always the
yours in? I
place.
don't have an HDMI port.
The pressure boundary is the place where all the sealing should occur, and it sets garages and conditioned space from the gas barriers, and also the thermal and pressure boundaries need to be aligned. Okay, let's talk about the thermal boundary. The thermal boundary is what is created when we put insulation up against our air barrier. So we have to have a continuous air barrier with insulation on it touching the air barrier in order to create what we call the thermal boundary. If we have an air barrier here and no insulation between the walls, there's not an actual thermal boundary there. There's a break in the thermal boundary. If we have a chase that goes up into the attic from the downstairs where the ducts are going through, and there's an opening there, that is a break in the thermal boundary if insulation is covering it. Anywhere where you go into an attic space and you see insulation, but there's a hole underneath and it's not making direct contact with the ceiling or walls, that is a break in the thermal boundary. So the plane of the building surrounding the space that is intentionally heated or cooled needs to have insulation up against the air barrier that creates the thermal boundary. The thermal boundary is going to restrict or slow the heat transmission through the building enclosure. It cannot exist without an air barrier, and it's a necessity for an energy efficient building. So thermal boundary is something that is broken in a lot of houses we go into. And even if it's just from batt insulation that's over wires in the attic and it's not making good contact with the drywall, that boundary is broken and we have a gap between the insulation and the air barrier, and there's no R value there. Okay. Thermal boundaries can exist in different spaces depending on where the air barrier is insulated. So we go into houses like this all the time. You have house A with an attic space, and house B, I was in one of these yesterday, no attic space, virtually flat roof. Unknown how much thermal boundary they had in there. I looked at it with the camera. There was something up there. But it's going to depend on where your air barrier is. So thermal boundaries can exist in different spaces. And they're going to be influenced by air leakage. So air leakage is really the biggest thing that we need to deal with when we're working on an old house and have an understanding of how it works. So this particular thing, I love going in houses. When I walked into this house and it was being remodeled and the bathroom looked just like this. And a home performance guy, when you walk into a room like this, it's just like, wow, I can see inside the walls. It's so awesome. But this house had a huge problem. And if we could tell by the assembly here, we see that there's paper backing here. So this is obviously an outside wall. There's flashing here and flashing here. And you can see the angle of the flashing going up here. So what this was is this bathroom was actually backing up to a cantilevered roof in the front that was actually going up the side of the California for the garage. So this is all attic space right behind here, behind the connected to the garage attic. So what we see here is a direct pathway for air to get inside the walls. And you can see if you look really closely here, there's like little dots where they took the old insulation out that had been stapled in there, and there was no air barrier between that insulation and the building assembly. So what could potentially happen here is you're cooling your house off here. These walls inside are cool, and it's drawing hot air, because remember that second law of thermodynamics, heat is always going to come to cold. And so we get cool or hot air translating up inside these walls. So they were never able to keep this upstairs, this entire wall. There was 2 bathrooms and a bedroom on this wall, and it was all connected like this all the way through. When we found this problem, I was able to talk the contractor into actually taking all the drywall off 4 feet up across that whole side of the house, and we ended up sealing this whole cavity off. What we found also was there was leaks here. So it was also open to here. So we had to seal all off as well, because this attic was also attached to the center floor area. So virtually what was happening here, because of this attic connection, this wasn't a 2-story structure that had a pressure boundary. It was really 2 1-story structures floating on a broken pressure boundary, and hot air getting in between the floors. And they wonder why their bills were huge and their upstairs would never cool down. So infiltration and exfiltration. these are the driving forces that move air. This is that law of thermodynamics that if you leak something out over there, it's got to come in from somewhere else. So air flows in and out of our building enclosures through different kind of construction flaws. A lot of times it's flue pipes. The air leakage in the building represents 5 to 40% of the space conditioning costs. When we do load calculations, we can actually see how much the infiltration is causing on our system loads. And then a lot of this is going to be driven because of ductwork changes in the house as well. So if you have your ductwork in the attic and it is leaking supply air into the attic, and you have a return underneath the furnace, that is going to create infiltration because we're pulling more air into the system than we're putting back out. We're leaking some air above the pressure boundary, which means we're pulling a negative pressure on the inside boundary, which means that's going to cause infiltration. So supply leaks lead to infiltration. Return air leaks, if you have a return in the attic, or you have an uninsulated or unsealed return air cavity that's connected to the interior walls, that's going to create exfiltration because you're not pulling as much air out of the house as you're putting back in because it's coming from other places. So it's going to incidentally pressurize the house and cause the conditioned air to leak out. So which would we rather have? Would we rather have our conditioned air leak out, or would we rather have infiltration where we're sucking in dirty air from outside and maybe in the attic and underfloor? And the jury's kind of out on that. It depends on what home performance guy you ask. But my opinion is we need to get it balanced as possible. If we have a very low differential and our ducts are tight and our return air is sealed well, we should not have infiltration and exfiltration dramatically that's caused by the ductwork. So that's something that's really important to understand is supply leaks cause the house to infiltrate. Return leaks cause the house to exfiltrate. So fixing air leakage in the house, how hard or easy can it be? Sometimes we work in a lot of older housing stock, and this is typical. And you guys that have been in a lot of attics know exactly what this is. This is a built-in China hutch in a craftsman style home. And you can see that they put insulation up here. So we had an insulation guy in this attic at one time that really didn't know what he was looking at. I think some of this we actually found insulation over, so it was a broken pressure boundary anyway. But when you have this open to the attic space, all of this wall area that's connected to the living space downstairs is all uninsulated, broken thermal boundary. When we have the opening at the top, it's also a broken pressure boundary. So how do we fix that? We fix that by foam board and foam ceiling. This house was, we'll talk a little bit more about this particular house in a bit, but we were able to make drastic changes on this house just by air sealing it and stopping the air from moving through. When you're electrifying, we must close up open walls, combustion vents must be sealed. If we're taking a furnace, excuse me, out of a furnace closet and we're sliding a new heat pump air handler into there, we need to take that opportunity to close off the intake and exiting combustion vents. We need to seal around the base where the drywall doesn't quite meet the plywood. We need to seal around that. We need to seal around any penetrations coming through the walls. We need to bring that closet back into the house, because when you have a furnace closet with ventilation, upper and lower combustion air, that closet is theoretically outside the building envelope. It's really existing between the attic and the underfloor. And sometimes we go to those things and we have an ill-fitting door. Sometimes you go to one that's really nice and they thought it out. It's got some weather stripping on it at least. Like this one had some very poor weather stripping on it. But we need to bring that closet back into the house, and that'll eliminate a massive air leak. So the other thing is we need to get into these return air cavities and seal them so that they're not connected to the rest of the house. This is an interesting home that we did here in Vacaville, and they had a big giant unit in it. It was a 5-ton system, and the house was completely uncomfortable. They couldn't figure out why. They had 4 bids for various different kind of heat pump systems being installed. But the one thing all the other bids had was nothing talking about any of the repairs of the actual envelope. And so we found in this house that this was kind of unrepairable, and we just got rid of all this, sealed this up so it was no longer connected to the house. Part of the issue, you can see that this is a return air filter grill opening. And if you see this right here, this is how you had to access under the floor. You had to crawl through the return air opening to open the hatch to get under the house. So there was no way we could seal this off permanently. But we were able to get and seal all this so it was no longer leaking to the house. But this was a 2-story, as you can see the ductwork going up. What we ended up doing on this one is we put a small 18,000 BTU slim ducted unit in the attic space for the upstairs. So we changed that zone, and the downstairs had a rather open floor plan. So we were able to do that with just 2 wall mounted units on 2 separate outdoor units. So we had a separate outdoor unit for the dual zone downstairs and a separate single zone unit for upstairs. But we were able to get rid of all of this, seal this, and the house is so still and tight and energy efficient now, and they're super comfortable. And we were the only people that came up with a solution to actually fix this problem. Everybody else just wanted to come in and throw new equipment in and hope for the best, not understanding what they were looking at. So it's really important that you take home performance into account. Okay, insulation problem. We run into a lot of insulation problems out there. And this is a pretty interesting picture because we have a lot of things going on here. We have compression, we have voids, we have areas where other insulation is kind of stacked on top of the other stuff. We have voided areas around around different penetrations in the ceiling, and just not real good consistent coverage. You can see here in the picture, this is the upper combustion air vent for the furnace that was below in the closet here. That was eliminated, and some interesting ductwork here. And then insulation problems also exist, under the floor. When you put insulation underneath the floor, the moment you install it, it's already trying to work its way down. Gravity is working on that stuff immediately. So it needs to be done really well and with a good suspension kit of some sort. So insulation problems can also exist because people don't understand what they're doing. And so this is a house that I found in Vallejo, probably, I don't know, 8 or 9 years ago. And what they had was a very hot upstairs. This is a knee wall that's in a remodeled attic space. This is one of those old Victorian houses with a really tall roof. The people before them built a room up there. So you had like these access doors and these knee walls. And of course they put plywood in there to store everything. Well, this customer, in an effort to try to fix this, called the local insulation guy. The local insulation guy said, "Hey, you should foam the underside of the roof." So they called another company out to foam the underside of the roof, and the company obviously didn't understand what they were doing. So as you can see in the little isinglass here, this whole roof has been underfoamed everywhere. But underfoaming the roof means we are moving the thermal boundary to the roof, which means that our pressure boundary needs to exist within that, between the house and that space on the roof. So anything in this attic space needs to be sealed 100% tight if we're going to move our thermal boundary under the roof. And so I don't recommend doing this on old houses anyway, because it's too hard to seal a space like this. But you can see they left the attic open here, which broke that pressure boundary. So it did no good for them to raise the thermal boundary to under the roof. It had absolutely no influence. Might have been reducing the BTU transfer through the roofing material a bit, but it's still, the attic was still extremely hot, and it was still a hot attic. And so before I took this picture, all these knee walls had no insulation on them. So what we did is we came in and we put R13 insulation with R8 FSK backing, and then sealed it with tape, and you see a little bit of poking out of the top there, but made a new air barrier behind the insulation and installed a really good insulation blanket against the air barrier in the house, and that fixed the problem. And the insulating these walls was a fraction of the cost that they paid to do it wrong in the first place. So it's important to understand how all these things align before you make recommendations, like putting insulation up under the ceiling, or excuse me, up under the roof rafters. I notice in a lot of new houses now they're doing ceiling and roof rafters, which is cool, and it can be done in a new house because you have control over everything. But when you're climbing through the attic space of a 100-year-old home, there's no way you're going to be able to seal this entire attic space. And then as well, that should have been insulated with foam as well if they were going to try to do it. So just a major problem there. So let's talk about R value as how it pertains to insulation. So R value is talked about as I have R19 in my walls, but what does it really mean? So R value can be communicated to a customer as degrees of differential. So if you have R50 in your attic, if you have a good R50 in your attic, it means that your attic can get 50 degrees warmer than your house before it's moving any significant energy through, right? That law of thermodynamics again. We've slowed that energy flow down to a 50-degree difference. So if you have R19 in the walls, it means that when you calculate in your drywall and whatever your outside siding is and figure out the U value of the assembly, we can figure out how much temperature differential there needs to be on the inside and the outside, and how much energy is going to move through, or what the temperature is when the energy starts moving through. So we talk about that a lot when we're looking at attic insulation, because this is one that we can talk about with our customers. The attic insulation is super important, especially if there's ductwork up there, because we want to bury that ductwork if we have the opportunity. We'll talk about that in a minute. But the resistance to heat flow can be communicated as 1 degree resistance per R. R50, 50 degrees resistance. If we think about that for a moment, if it's summer and we're keeping our house at 75, do the math in your head real quick. 125 degrees, it has to be at least 125 degrees in the attic before any energy is moving through. If you have R10, it only needs to be 85 degrees in the attic before the heat starts moving through. And it's mostly 85 degrees in your attic all the time, right? Unless it's super cold outside. So the more insulation you have, the better. And we're building a blanket to separate us between the attic temperature and the home temperature. This also works in reverse. In the wintertime, when your attic is extremely cold and your house, you want to heat your house to 70 and you got R50, it has to be 20 degrees up in the attic before you're going to move before any of that heat's going to move up through the top. Okay, hopefully everybody understands it. Okay, calculating duct gain. There is in the Sacramento area and generally this area of California, there is a lot of houses with ductwork in the attic space. And this is one of the easiest ways you can calculate what your capacity savings can be by replacing and burying this ductwork. And we see this very picture up in attics a lot. You go to an older house and you look up there and you see a return air that's raw metal. And it gets to be 125 degrees, very conservatively in the attic space, and you've got raw metal there. That return air turns into a heater. So now all of the air that's coming through that return air is getting preheated before it goes into the system, and the system has to use a specific amount of its capacity to offset that. It's the same with supply side. So if we pull our return from the house and we run it through our system, we condition it, there's a certain amount of loss that's happening in the ductwork on the supply side in the attic space because of the temperature differential. And we're going to show you how to figure that out. So the way that you figure out duct gain is there is a BPI standard that if we went and took all the ductwork out of a typical attic, the internal surface area of that ductwork would be about 40% of the square footage of the house. So for quick perspective, if you have 1,000 square foot house, you're going to have about 400 square feet of internal duct surface area. Okay, so we always use in all of our trainings a 1,500 square foot house as our trainer. So if we take this 1,500 square foot house, we just take a very conservative 125 degree attic. And any of you guys that have done HVAC work in Sacramento know that 125 degree attic is a cool day in the summer. Okay, and we want 55 degrees supply air coming through because we want our house to be 75. We've got about a 20 degree split. We'll say that's pretty solid number. And then when we have R3 insulation, now R3 insulation is going to be metal ductwork with yellow insulation around it, or various asbestoses, or not well installed R4 insulation with like the Y branches. R3 is a good factor. Now, what we're being very conservative on this 125, and so our R3 is going to be very accurate. Okay, so let's do the math on this. So with R3 ducts, I'm going to take 1,500 square foot house, times it by 0.4. That is going to give me my square footage. Away the answer. That is going to give you our internal surface area. We times that by the temperature difference, which is 125 to 55. That's going to be 70-degree temperature difference. And we divide that by our R value. So this is 42,000. We're going to take 1,500 times 0.4 times the 70-degree temperature difference. That's going to give us 42,000. We divide that by 3. So that's 14,000 BTUs, 1.2 tons of cooling capacity that's being lost to the hot attic space. Now, this is a very conservative number, again, because we have 125. Obviously, if we have R6 ductwork in the attic, this number is going to change. These numbers are going to be a little bit different. If we want to use a more accurate number and say, hey, on the hottest days of the year, my attic is 140 degrees, you can do that measure as well. But this is a great way to communicate to the customer and to understand how much energy we're using and how much capacity we're using just to keep these ducts neutral. So in this particular application, we're going to use 14,000 BTUs of cooling every hour to keep those ducts neutral. That's a lot of BTUs. How much is that? That's a lot. So if we bury the ductwork, so say let's replace the ductwork, let's lay it down low, let's do a nice job, seal it up, pull it tight so we have as little duct material in the attic as possible. So we do that. We bury that ductwork with R50 insulation so that we get a good burial around the sides and about 3 inches on the cap, at least around everything. We're obviously not going to be able to bury like an 18-inch return air or a 16-inch duct totally. So this is an average. If we bury everything in R30, we're going to only lose 1,400 BTUs. So that's 0.1 tons lost to the attic. So just by burying our ductwork in this 1,500 square foot home, we're able to save 1 ton of cooling capacity, right? Over 1 ton of cooling capacity lost to the attic space. So we can go in and improve the attic space and improve the ductwork and reduce the capacity of the system by doing so. The other things we want to consider is, what is the benefit that we've just gotten from putting in R50 in the attic space? So we also are going to reduce our load capacity by doing that. So we won't go into how to do the U factor. I'm sure all you guys can figure that out. But U factor times square footage by temperature difference. So what we're looking at the ceiling heat gain. And if we have our same 1,500 square foot house, the attic is 125. We're cooling the room to 75, which gives us a 50-degree temperature differential. Just do the math there. If we have R10 insulation, and R10 insulation is really, if you can see the rafters, and it's kind of not good and there's gaps and stuff everywhere, I use R10 as that benchmark. If we've got cellulose that's perfectly installed all the way up to the top of the rafters, might be a little bit more, but you can figure that on the U factor. But in this particular application that we were looking at, we take that, we do 1/10, which is our U factor of R10. We times that by the square footage and times that by the temperature differential. And that gives us 7,500 BTUs per hour that we're driving down through the ceiling with R10 in a 1,500 square foot house with that 50-degree temperature differential. So remember, 50 degrees, 75 in the house is what most people set their air conditioner to, and 125 in the attic is not that hot really in Sacramento in the summer. So your numbers may vary. But 7,500 BTUs is being radiated down from the attic space every hour in this house. So if we do that same R49 insulation and in that same 1,500 square foot house, we're burying that ductwork, so we're getting that initial benefit of reducing the capacity on the air conditioner there. And then We're also reducing our radiated capacity through the ceiling from 7,500 to 1,500. So what did we save there? We just saved another half a ton of cooling. So this is how we, a lot of times, are able to take a 3-ton system out of these houses, put in new ductwork, bury it, air seal a little bit, and we are able to condition these homes with an 18,000 BTU inverter system with no problem. They work fine. Now, I know that's a hard one to swallow. The first few are going to make you nervous, but believe me, it works. Okay, so please put any questions you have about this in the chat, and then Alex will answer them. We should talk about any questions you have with this, because if it's not clear, it needs to be. All right, so really high performance enclosure specifications. If you were to consider a house a high performance enclosure, this is what you would need. You would need 0.5 CFM50 per square foot on a blower door test. Most houses are not this tight. As a matter of fact, when we test houses, a lot of the houses we test are 2 CFM50 per square feet. So if it's a 1,000 square foot house, oftentimes we have 2,000 or more leakage CFM50. If we can get a house, and this is kind of what we shoot for, if we can get a house to 1 CFM50 per square feet, we're thinking that's a pretty good envelope. But high performance is 0.5, so half that much. Attic bypasses and unsealed interstitial cavities need to be identified with an IR camera, and you need to verify the window performance, and the window performance needs good. Now, these are high performance enclosure specifications. Most of the time, you can't do high performance enclosure specifications unless you're doing a massive retrofit or building a house. So high performance electric home HVAC ducted mini split specifications. We want to have our SEER ratings really high. Our heating HSPF should be above 12. Our heating capacity, 10 BTUs per square foot. Now think about that for a few minutes. This is high performance. Most jobs out there never meet high performance specifications. Even the jobs we install aren't quite all the way here, unless somebody wants to spend a lot of money. So duct insulation always should be R8, buried in our case. Our duct leakage should be less than 5 CFM, and all the temperatures in the room should be within 3 degrees, and we should not have more than 0.15 static pressure with clean filters. Now, these are high performance electrification specifications. These are not things you're going to be able to do in a typical home, but this is where we're looking at as the benchmark. So we can get to the bench, we can get somewhere in between what we're doing now and the benchmark and make a lot of improvements. Okay, unitary. So same as ducted mini splits. Good unitary high performance is going to give you delivered cooling EER of 12, measured sensible EER of 90% of 12. We always want to have a heating HSPF of over 10. That's hard to get on unitary at 16. Cooling capacity, 1,200 square feet per ton. Most of us aren't shooting for this. Typically, our systems are between 695 and 1,000 square feet per ton, and we're only doing retrofits. Verified refrigerant charge. Return air grills should always be at least 600 square inches per ton with high performance. That's something else that's not getting hit out there. And we should never have our system standby watts more than 10, and the rest of the stuff. Always, the bigger return air grill and the bigger return air duct you can put on is going to give you the lowest static pressure. And you can do 0.25 water column with clean filters with a heat pump. It's really, really hard to do with a furnace and a coil. Heat pumps are easier. Okay. So let's go into the unintended consequences of box swaps. And so a lot of heating and cooling systems are sold by maintenance technicians and service technicians. And that's kind of the way the industry has worked. And it's been okay the time that we've been doing furnaces and air conditioners and you're taking out one and putting in another. But if you're doing that, the customer needs to know you're doing that. Like, I'm taking out your system and replacing it with another system. Mr. Customer, you know there's a better way to do this. This is the fast way to do it and probably the least expensive way. Are you okay, or would you like to learn about the better way to do it? And that's the problem, is that never happens. So we run into this problem with systems being changed out like for like. And so a lot of homes that were built in the 70s no longer have the 70s windows. They no longer have no trees. They have a little better insulation maybe, or the customers have remodeled some things and made it tighter, or whatever. But most houses from the 70s aren't existing the way they were when that system was installed in the 70s. So for us to take a system out that was installed in the 90s because it replaced the exact size of the system from the 70s, and we're going to go ahead and put the same size system in now in the 2020s, uh, that's not that's not good business practice. It's not good electrification for sure, and it's not something we should be doing with heat pumps. We know with a house that's 1,500 square feet, we usually have a furnace in there that's at least 60,000 BTUs. Uh, 40 to 60,000 40 to 60 BTUs per square foot. There's a ton of waste heat on these systems. So because they're way larger than they need to be, people don't notice that they don't work well. So these systems always short cycle in mild weather, so the furnace just runs a little bit of time. And a good rule of thumb that I use all the time is if you have a customer that says my house heats really well, it warms up in 10 minutes, or it gets hot in 10 minutes, that's not a properly sized system. So the best reliable solution for unitary is really two stage, which is also not that reliable. Two stages are usually 60% low or 100% high, and the low stage on a 60,000 BTU is just 36,000 BTUs. So that's going to match what your heat pump would be all the time. Okay. So trying to plug and play heat pumps, trying to pull a gas electric system out and plug and play a heat pump, it can cause major problems. And companies out there are seeing this now. Like they're seeing customers complain about high bills, noisy systems, it's blowing cold air on me. It's not what you explained it was going to be. It's not saving me money. There's a lot of challenges in installing heat pumps properly. So good thing y'all came today. So we have a lot fewer BTUs to deliver with a heat pump. We need to make sure duct sizing is right, and putting a new reduced capacity heat pump system on old ductwork that we're not checking and verifying has the right capacity is problematic. We need to have proper velocity for air mixing, and we need to keep the air from blowing on the occupants. We need to change the registers in these houses, people. When you're installing a heat pump in a house, especially with ceiling registers, and you keep those three-way registers in there, when this heat pump is heating the house with air that's very close to the temperature of the room temperature and very much cooler than your skin's temperature, it's going to feel like cold air blowing on people. We can't blow the air on people with heat pumps. Change the registers. We're heating with much lower temperature, so it can feel drafty. Defrost cycle screws up winter performance, and kind of the common solution for this has always been we put a heater strip on here that kicks on during defrost, which is also going to kick on anytime the temperature gets below maybe 39 degrees, because we're going to be slipping and we're not going to be able to keep up. So we're bringing this electric strip heater into the play, which is driving up the energy costs in the wintertime. And even if the heat pump can keep up when it gets colder outside, it's going into defrost more often, which is bringing the heater strip on more often. So we have all these problems using all this energy. We can miss all this stuff just by sizing stuff right and using the right equipment. Panel planning. When we go out to a house that has we as HVAC professionals go out to a house that has a furnace and air conditioner, and we put in a new heat pump system, and we add a strip heater, and we add a new line, or we recommission the dedicated circuit to the furnace as 220, or in some cases I know they've got these 110 blower assembly things now. So that kind of solves one problem. But what we're doing is we're adding load to the panel instead of reducing load to the panel. So if we can take a system, in my house, I had a 50 amp breaker going to a 4-ton unit on the outside of my house. my new heat pump that I have in there only needs a 20 amp breaker. I was able to free up capacity to do other things in my house because my new system used so much less energy. And it's the type of system where the outdoor unit actually powers the indoor. So I'm powering the indoor and the outdoor for 20 amps, where just my old outdoor unit had a 50 amp breaker. So panel planning is extremely important because these customers are going to have, sorry about that. These customers are going to have to get other things taken care of as they electrify their houses. Okay. Educating customers is super important, and it doesn't get done when we're talking about, hey, I can get this system installed for you next week, and it's a 3-ton system. We're pulling out a 3-ton. We're going to put it in a 3-ton heat pump. When that happens, you don't have time to do a load calc. You don't have time to calculate the ductwork. You don't have time to do any of that. And so that's the way the industry is going. We need to get away from that when we're converting to heat pumps. Okay, furnace outputs. For years, I was doing this as well. I've been in the HVAC industry for 40 years, I told you. I've been doing HVAC sales for a lot of years. And so back when they had these 12.5 incentives for EER, there was like a $250 or $300 rebate, but we were selling systems for $6,500, $7,500 back then. $350 in perspective was a decent little rebate somebody might want to get. And they also had rebates at the time for high efficiency furnaces. But this is typical of what we had to do back in the day. So I have an outdoor unit. I don't know, some of you guys may recognize these numbers, but what this is this is a 410A. So this is the modern refrigerant. This is an 18 SEER, 24,000 BTU outdoor unit. And I don't need to tell you what brand name it is. If you recognize it, you may recognize it. So this unit is combined with a 31 slab coil, 24,000 BTU. But in order for me to get this unit, which was sold as a 18 SEER, it said on the front of the brochure as high as 18 SEER. So in order for it to be sold as an 18 SEER and just meet this 12.5 EER, the furnace we had to combine this with was massive. So this was an upflow furnace, 2-stage, 80,000 BTU, variable speed 4-ton. So in order to get 12.5 EER, and when I went and looked at all these, I was trying to find the match that had the highest rating with this particular outdoor unit in this size. So I even did a small outdoor unit. But this unit never did achieve 18 like it said as high as on the brochure. It was 17. And in order to get the 12.5 rebate, we had to put a furnace in that was literally 3 times larger than the capacity of the air conditioner, which in California never comes up unless we're going in the mountains somewhere. So we were buying these systems with massively oversized furnaces just to get people rebates. And we didn't know when we were doing that what the negative effect that was on the home. Now we're going back and correcting some of those situations. So we need to be real careful with that. Over here we have this is a inverter mini split system. This particular one I think is a ceiling cassette, I'm not sure. But I just happened to pull up this ARI certificate. With this one we can achieve really high EER, really high SEER, have multiple heating states, a really high HSPF rating, and we're doing it with 18,000 BTU. So we're able to achieve the lack of performance we would get out of this system can easily be made up in a inverter system. So look at inverter equipment. It's really good option to replace unitary, and it's less expensive. Okay. Sizing, the most important step. Smaller systems use less energy and cost less to install. So if I'm up against doing a change out, like a service tech goes out and says, we're going to put in a new furnace and air conditioner, 3-ton with a new coil. I don't even know. I don't do any of that work anymore, but that's a specific amount of money for that equipment. If you look over at what's available with inverter equipment, like with the mini split based ducted equipment, they're very inexpensive in relation to that. And we can really ramp those up and make them perform better much more easily than you can a traditional unitary system. So you have a lower cost of installation. Bigger systems are going to cycle too much in milder cold and warm, milder cold, and also just mild warm days. If we size a system to achieve full capacity, just happen to have this load calc in front of me. If we have to size a system to achieve full capacity, this particular load calc I'm looking at, I did yesterday. This is sized for 104 degrees. Most of the summer it's not 104 degrees, but you want your system to work when it is 104 degrees. So we size it for that. So if I'm sizing a single stage system to cool your house when it's 104 degrees outside, what's it going to do when it's 89 degrees and you just want the house to be cool? It's going to be way oversized. It's going to turn on and off a lot. It's going to pull a lot of locked rotor amps every time it starts up, and it's going to waste a lot of energy. So if I have a system that will give me the maximum output I need on load calc days, so I can design this thing to do what it needs to do on the hottest, coldest days, but it also has the ability to slow down and meet the requirement for all the other days of the year. So in real time, it's giving us the exact capacity we need. Is that going to be better or worse than having a system turns on and off all the time? So loose houses, um, when you have a loose house and you don't do anything to tighten it up, it needs more capacity, which means larger systems. So when you go in and do some of this basic air sealing, seal underneath the bathtubs, seal underneath the plumbing penetrations, and seal the wire holes in the top plates in the attic, you've got a pretty tight house. Seal your interstitial wall cavity if you have one. If you do all that, you need a much smaller system. To do all that and put the same size system in is malpractice, because now we've made the house theoretically smaller and we put a system in that's way too big for it now. So understand every room needs a different amount of air. So a room on the corner of the house is going to need more air than the same size room next to it. We'll talk about that in a minute. Doing this wrong will cause lack of comfort. So when you have a system that turns on and off all the time, or overheats and overcools, it's not going to be very comfortable. Before I put my heat pump in, I did a tightening on my house. I tightened up put new ductwork in, insulation, air sealing, windows, and I kept my old system in because I was a cheapskate, and it was only 5 years old when I did it. And finally, like 2.5 years ago, I changed that system out and put the heat pump in. But we were running our air conditioner at 80 in the house because it got so cold when the thing came on that I couldn't stand for it to run long enough to get the house any cooler. It was uncomfortable. When the furnace was sized by being in low stage, and I turned down the gas as far as it would go and still light. So I don't even have any idea what BTUs I was at, but it was still too much. So I ended up taking out that system, and I just have a 30,000 BTU system in there now that'll go all the way down to 12,000 BTUs. So it gives me the right size system for whenever I need it. Okay. Why BTU to kilowatt is not a reliable sizing method? We're seeing this out there of what they call peak heat or peak gas, and sizing a heat pump for the peak gas usage for a month. Now, it's a good way to verify a regular load calc, but what it does not do is consider the homeowner's habits and their efforts to save energy. So as air conditioning and heating people, we know we've gone to people's houses. They say, I haven't used my furnace a lot because I don't like burning natural gas, or the bill's been really high. So if they didn't run their system a lot the year before because they were conserving energy, and we matched their heat pump to the peak BTUs, and their peak BTUs are artificially low, that's not going to give us a good match. It also does not provide room by room load requirements. It doesn't consider multiple room options like mini splits, and it won't ever come undercover problems. So if you've got an old furnace and we're using peak BTUs, and it's got really old leaky ductwork, and they were just wasting a ton of energy but staying warm, if we size to that, we're going to put too large of a system in because of the inadequacies in the existing system. So it's a good way to kind of double check, but it's not a great way to size a heat pump. There's too many unanswered questions there. Okay. All right. So heat pumps in California, big opportunity or big risk if we screw it up. So 90% of California homes rely on gas for space and water heating. There's 12 million houses out there that have gas or electric resistance and water heaters, but there's 3.4 million houses out there with no air conditioning in them. So if we're going to electrify and change out gas heating systems in houses without air conditioner, and we have a heat wave like the East Coast has had, or Texas has had, or we had in the central part of California or part of the United States this year, if we have that and we have a lot more air conditioning units online than we did before, and a lot of them aren't installed well or they're too large, this extra 3.5 million houses coming on with air conditioning is going to be devastating. So I think SMUD did some research recently. I don't think that slide's in here, but SMUD did some research recently, and they found that by putting inverter systems in, we overall reduce the amount of energy needed. By putting heat pumps that are non-inverter in, we were increasing the amount of energy. So if just everybody took out every single stage air conditioner in California and put in an inverter, we wouldn't have to worry about the grid because we'd be using less energy than we're currently using, even with 3.4 million new houses online. So we need to do this right, folks. Okay, I've preached there. Okay, so real load calculations. So really, okay, real load calculations are not rules of thumb. Unfortunately, in the HVAC industry, we've gone to this whole 400 square feet per ton, and I did it myself for years. And I know this is an old rule of thumb because I was doing it when I was really young, and I'm not young anymore. So when I got doing BPI, I learned about load calculations. We started doing load calculations, and we started understanding that every system we were installing was too big, and that you can't go into a house in the 1970s where we said 400 square feet per ton, and the people put new windows in, insulation in, they've tightened the house up in various ways. They now have a shade and shade structures and all these things around their house that's grown in, and still say it's 400 square feet per ton. You can't do that. So the only way that you can know based on everything that's been done to the house or you're going to do to it is to do a load calculation. It's really the only way to do it. This is a load calculation on a 1,500 square foot house in Fairfield, California. And there was a 60,000 BTU furnace in this house and a 3-ton air conditioner, which is typical for a 1,500 square foot house. That's what they all got. This house was built in 1954. The system we pulled out was from the early 2000s. Late 1990s, I think, like a 1997 system. So that means that it had a system in there before that, and somebody came in and put this other system in, either using a rule of thumb, saying it's a 3-ton house, it's a 1,500 square feet, 500 square feet per ton, we need a 3-ton system, and that's what they put in. We came in and actually did the load calculation. Now, what this customer had done before we came out to the house is they installed all new windows. There was a shade structure back here. And we insulated the attic space once this was all installed. We, as in the company I worked at when this was done. This was a number of years ago. So we did a load calculation on this house. The only assumption that we built into this load calculation, other than what was really here, was the attic space that we were going to insulate, and we actually calculated these ducts being inside the building envelope. So we only needed less than a ton of cooling and 18,000 BTUs of heat. And in Fairfield, it gets really warm. So we were thinking, this is odd. We need this. So what we did, we put an 18,000 BTU slim duct vertical system in the closet here, ran these ducts inside the envelope. This one kind of jumped over here. And we only needed 423 CFM air movement. And so this system has the capability of going up to about 21,000 BTUs when it needs to. 26, I think, on heat, but it's never ever been a problem. And they kind of just leave it on and turn it on and leave it on. So the concept is real easy. So how would you know this? If you're using sizing and going, and what another thing that we hear in the industry is air don't care. That's something that people actually say. And the other one is small room, small duct, big room, big duct. So what does that mean, right? So if a contractor came in and said small room, small duct, big room, big duct. Here we have 2 rooms that are the same size. One of them needs 50% more airflow than the other one needs. We know why by looking at this. If we understand, it's got 2 areas of influence. Mother Nature is existing on 2 sides of this room. So every house that has a corner bedroom needs more airflow than the bedroom next to it that only has 1 wall. So you can just know that. Is it enough to change duct sizes? No. The same size duct went to both these rooms. We just had to put a damper on and damper it down. But this is not always done. if we would have put the same size duct in here and kind of let it flow without balancing it, sometimes you might have had 75 CFM in each one of these rooms. Both these rooms are going to be unconditionally or uncomfortable, and one's going to be worse than the other because this one has so little load on it. So it's important to know this stuff, and the only way you can find out is with a load calculation. If you're not calculating, you're just guessing. Okay. Swapping like for like sizing, existing 1,500 square foot house, there it is again. 3-ton systems mostly have 60,000 BTU furnace. The new heat pump is going to be 40% less heating capacity. And heat pumps lose a lot of capacity when it gets below 40 degrees outside. That's why for years we've combined them with furnaces or strip heaters or backup heat to kick in when the temperature gets lower. If you're putting in a heat pump system that needs some alternate heating because it's going to be cold outside, you're not putting in the right heat pump system. Stop doing those. They have solutions that you don't need to do that. And we don't need to put in something that's going to use more energy for the same solution. So if we do this and we have a system that cycles on and off, it's possible as it's getting really cold outside, this unit is not going to be able to keep up on the next cycle if the outdoor temperature drops below 40 degrees. It might not have enough capacity to warm the house up again. So if we have an inverter system and we're keeping the house warm, it doesn't really matter because the house is already warm. So the unit just slows down or speeds up to take care of the load, and the house is already warm. It's when you let the house get cold and it drops below 40 degrees outside where these units won't work. That's when your customers get really mad. Okay. Replacement of the system without planning. This is a problem too, is like emergency replacements for heat pumps. We talked about this a little bit before with box swapping. Box swapping is more of a, like, somebody calls for an estimate and you're just going to put a heat pump in. This is I got a service call, the heater's not working, I just sold them a heat pump. So maintenance and service technicians, I love you. I am one. I've been a maintenance and service technician my entire career. I'm really good at fixing stuff, not so much anymore because I sit in the office all day, but maintenance and service techs and are not designers. They're not always up to speed on the best technology. I don't want to say this, but this was the way I was when I was there, is we were looking for a quick sale. I worked at a couple of companies over the years that were commission driven. They were commission only. If you wanted to be able to make any kind of a real good living, you had to sell stuff to people. And I'm diametrically opposed to that now, but I'm just out here waving my flag. My company doesn't operate that way now. So unfortunately, when systems are being sold on service calls or on maintenance calls, they're looking for a quick sale. Usually it's going to go in the next few days and you're going to get paid for it on the next paycheck, right? So we call that sold on Monday, installed on Wednesday, paid on Friday. It's the way a lot of companies work. It's your business model. I'm not going to say anything bad about it. It's just not what we do anymore because it is. Okay. I don't want to apologize for something. So unfortunately, most of the guys are looking for a quick, easy sale. We don't have a lot of time to design anything. And a lot of those technicians are so busy out being technicians that they don't have time to understand some of the things that your designers or salespeople or yourself on this call might know. So we need to have our customers understand that if you're switching to a different technology, we need to take a little time and design a proper system from you. Otherwise, these customers could end up with energy guzzling systems, be very upset, and not be comfortable. So result of poor planning, rush to get systems back online, create rash decisions. What we do, I had a customer the other day, their air conditioners broke. We're able to get them into the schedule in a reasonable amount of time. Get them into the schedule in a reasonable amount of time. We can't usually do that. So we will go out and get air conditioners working for people in the interim until we can get their system put in. Usually we're a couple of months out. Okay. Putting the wrong system can result in a larger load and unnecessary panel upgrades. We've seen a couple of these happen over the last couple of years where we come in to do another electrification measure, like a heat pump water heater. We had a couple of them show up that way. Customer had a heat pump installed by another company. A 1,200 square foot house, they got a super high-end inverter comfort system, unitary from Carrier, I believe, a 230 volt air handler, and a backup strip heater on a 1,200 square foot house that could have used an 18,000 BTU slim duct to do the whole house. But they put all this in, 6 breaker spaces, used for this system that was horrendously oversized, and they had to get a new panel upgrade to get the system installed because it was going to take 6 breaker spaces. Well, when we got out there, the panel wasn't going to be the right capacity because they didn't up the capacity of the panel. Now the guy wants a stove, a dryer, a heat pump water heater, and solar and batteries. He had to replace that panel and upgrade it to 200 amps. So the guy bought 2 new electrical panels in 2 years because he was steered the wrong way. So be careful about this. Knowledge is power. Okay. HVAC professionals with no experience and knowledge of envelope performance, they need to get updated on this. We got a couple classes coming up to this area in the fall. So we learned a lot over 3 days. Results in larger loads, unnecessary panel upgrades, talked about that. More drag on the grid in cold weather. Also, expensive to operate systems, people are going to shut them off and they're not going to want to run them, and they're going to wait till it's too late. They're going to try to turn them on when it's cold outside and it's cold inside. They're going to work even worse and use more energy. We need to put small systems in that are going to run long cycles. Okay, so how far should we go with home performance as a company? So it doesn't have to be super complicated. We go by this theory that there's no silver bullet to putting a system in great, but there's a bunch of silver BBs. So there's a bunch of things I can do small improvements I can make on the system. They're going to make a vastly improved system. So do a handful of things better and you'll be amazed at the outcomes. Take pride in your work. We can all do this better. We can even do it better. And we're doing a lot of extra stuff. Focus on these items. Get a load calc done. If you don't have the capacity to do a load calc, there's several trainings available through Tech Clean California that you can go to, and they will give you a license or they'll give you a certificate to purchase a license for the load calc if you go to the load calc training. So just do it. There's no reason why not to. It does take a little bit more time. Pay close attention to air distribution, the ductworks. They need to be sized right. We need to, when we're putting them in and resize and redoing them in the attic space, if you have the ability to shorten up those duct runs, put the outlets on the inside of the house blowing out so we can shorten up the duct run, that reduces the thermal mass that's in the attic and it reduces the amount of heat we're going to pick up. So pulled tightly, put in straight, short as possible, well insulated, keep the static pressure low. Put some elbows on those turns when they go into the boots. Put some elbows on the 90-degree turns as they go through the attic. It's not that hard. It costs a little bit more, but you can charge for doing better work. Air seal the major penetrations in the attic, like any interstitial wall cavities, wire holes, wall caps if you can get to them. Definitely anywhere where you've got a trunk line coming up through and you can look down in there and see an open space, seal that thing. Insulate over it well and install an inverter or a measured performance unitary system. Crew training. It's so much easier to train your crew to do stuff right if you test stuff while they're there. Some companies don't have the ability to do this, and I understand, but spend the time and get the HERS rater scheduled for when the job's going to finish up. So when they're doing the testing, your guys can be there to fix it. So if the installers test their own work and learn how to do it, they're going to learn from the test results and they're going to want to do better. That's working out well here. Home performance monitoring is expensive, but tracking the home's performance by analyzing utility bills is cheap. So call your customers up, ask them, how's my system doing? Understand how much energy they're using. Okay. Are we ahead of schedule right now, Alex?
We'll try to wrap up in the next 6 minutes or so. So,
Okay.
Yep, I think we're gonna have good timing here with the last case example.
Okay. So this is a case study on a house that I pulled. We went through a bunch of them, and I put this case study together. I like the case study itself. It's not a Sacramento case study, which we could have used a Vacaville, but this one's great because it's got all aspects of the job, and it was a house in the Bay Area, but it was actually, when we do load calculations down there, we find most of the time that the heating load is a little higher than the cooling load. This was a house that had a higher cooling load than heating load. They had the whole house was beautiful, but it was porous as all get out. It had really high infiltration, and it had all these south-facing windows and the big door here and all these south-facing windows on the top floor. And it actually came out that it had a higher load on cooling than heating. And you notice my latent load, super low. Okay, so we took out an existence big gas furnace, 80,000 BTU system. It was a 92%er, 72K delivered. The attic was really, really bad. It had huge envelope and air leaks. In fact, the pictures I showed you before of looking down on the china cabinet was one from this house. It was massive envelope air leaks. As a matter of fact, they had these doors that closed between the foyer and what would have been the sitting room back in the 1800s when they, or the early 1900s when they built the house. And you could literally look up there and see directly into the attic, and you could see directly down into the house from the attic. So huge. We fixed that all in 12 man hours and replaced the water heater as well. This is my son, 16 years old, up in the attic with his foam gun getting after it. Here's the picture of where the pocket doors were below, and you could actually see the room from below. This house had massive air leaks, coffered ceilings, holes between the walls, a bit of ceiling to do. And we were able to get a good, we charged enough for the ceiling that we made really good profit on it. It took 12 hours, and it was about $400 of materials to fix this whole attic. You can see we boxed in the areas that were over the china cabinet and the doors, foamed in everything, every space, all the coffered ceilings, all the gaps between it. We used about 12 cans of foam on this house. The installed mechanicals were a Bradford White 80-gallon or 65-gallon heat pump water heater, a complete designed installation of a mini split inverter heat pump. We ended up using, I gave them the option originally to put a system in the attic and another one downstairs so they could split it all off, but they decided to reuse the existing ductwork because it was on a system that was from 98. And the ductwork had been replaced during a previous remodel, so we went with that. We got rid of that 80,000 BTU furnace and put in a 36K Mitsubishi. This unit has the ability to do about 37,500 BTUs of heat and just right at 36,000 BTUs of cooling. This unit will slow down to about 16,000 BTUs. Nice inverter outside, air handler inside. Always when we install any inverter air-driven equipment, it's always got a MERV 13 Aprilaire filter on it. We always put the same filter in every job. So it's always a 2020 MERV 13 filter. So I know when a customer calls or needs a filter, I know exactly what's in there. We just use the same one every time. Modified the existing newer ductwork to be suitable for the heat pump location. And so this was the result from this guy. When somebody tells me I do great work for a reasonable price, it means I didn't charge enough. We had them install heat pump water heater, heat pump installation. They were super knowledgeable and informative about options as well as rebates. They also provided all we needed for the final inspection from the city of Berkeley. Both the heat pump and the water heater are working great and much cheaper to run. So if you guys are having problems with customers saying that their units are not cheaper to run, it's because you're not sizing them right or putting in the right type of systems. Okay, the heat pump is also much quieter than our previous gas furnace, and the extra insulation was added to be a major improvement. Even without the heat pump, our upstairs rooms are much more stable in terms of temperature, both summer and winter. So not only did we do all that, but we also reduced their run times and put in an extremely efficient system and made good money on it. The attic space was not an expensive operation to do. Actually, me and my son went up there and did it. So I would say, including some levels of home performance, air seal the big holes, make sure that the air barrier and the insulation is touching and making a good thermal boundary. Seal those holes between the crawl space and the attic space so you don't have broken pressure boundaries. Make sure when you're looking at something, you understand where the air barrier is and if the thermal boundary is aligned, like in those attic knee walls. Look at that stuff through a slightly more critical eye. Make sure that we're just not making recommendations because the next guy did. We see a lot of things where a contractor will see a bid, he'll say, okay, there's insulation on there, and we'll go back and find out. And I didn't really see this firsthand. The company I used to work at, we saw this a few times. a company would come in behind us and do the insulation. And we recommended burying the ductwork with insulation, resizing the ductwork, come back, do maintenance. There's insulation in, and the ductwork is hanging up in the high part of the attic. You got to do the stuff in the right order to make things work right. So home performance is really important for heat pumps. And ready to take some questions.
All right, very good. So our company contact information is listed there on the screen. If anyone has questions after the meeting, feel free to shoot us an email. I'm always happy to collaborate and assist. So Larry, a couple questions that have come through the chat throughout. First one from Lonnie. Had a comment about how a lot of, as we're starting to electrify, these devices are connected to the internet. And there are some issues that come up when devices reset and the internet goes out or the electricity goes out. So skipping ahead to a follow-up comment, on some of these systems, when the electricity goes out, do the system settings go back to default? My comment is that it sort of depends on the device. Some of them do and some of them don't. But what's your take on that question?
The majority of the systems that we install all have a battery backup in the thermostat. And so the thermostat is holding the programming. And then when you do these systems and it tells you to set up the thermostat, set the airflow functions, and do all that, and you set that into the unit, and then you go out and you shut off the power and you start it back up again, it resets with that in the memory. So we've installed hundreds of these things and never had that come up. So I'm unsure if that would be the case in most systems, but the ones that we're using, I haven't seen that pop up in the hundreds and hundreds of them that we put in.
All right. And a follow-up comment, a particular individual lives in Portland, had a question about what they should consider instead of a mini split because it drops into freezing. My comment there was make sure your contractor does a manual S and picks out an inverter system that can handle those temperatures that drop down into freezing, because those do exist. Or if it's extreme weather, you can consider doing dual fuel, but that's not something we do down here. And then there was a request if we have any contacts in Portland, Oregon who do proper design.
There's a company up there called the Heat Pump Store, and they kind of do what we do. And sub-freezing temperatures, I mean, if you're up in high elevations and you get a lot of snow, but sub-freezing temperatures, the number one adopter of heat pump technology in the United States is Maine, and it's super cold out there. By combining making your house a little bit more efficient or tighter and putting a cold weather heat pump in is going to give you far better operation than anything else that you can do. You could do something with maybe a furnace backup, but that's likely not the best solution. Your electricity is super cheap up there, and there's going to be degasification everywhere. So low temperature heat pumps are going to be the best. They have those in wall mounted style and ducted style. Just make sure your contractor is going to do a load calculation and design the system that's right for you.
All right. Next one, was hoping that you could elaborate further on the inverter comment with respect to the resulting impacts on the grid. My comment in response was, essentially the takeaway is that inverters carry higher overall efficiencies and they're going to match the energy expenditures to the actual load that's being required, rather than just running out a single capacity, which therefore requires that system to be oversized in most scenarios. So if we could take all of those single stage systems and have more dynamic and efficient systems, we could take the resulting efficiency to make up for some of the additional load that's going to come on the grid with new air conditioning, EV charging, etc. So it's not something we've done detailed analysis on, but just by doing so many of these systems and seeing the outcomes, we're very bullish on it. And it looks like SMUD is working on putting together a study that shows exactly what these outcomes are. So, Larry, did you have any additional comments in that regard?
Yeah, one of the things that we didn't show on this slideshow is we have a really good graph of how these work. And when you have an inverter system in your house, you should run it differently, and you should have your customers run it differently. So with an inverter system, they use a fraction of the energy when they're maintaining the temperature of the house as they do when they're heating or cooling the house. So if you let the differential in temperature get really high, say it's 82 outside and you want the house to be 75, or it's 82 in the house, you want it to be 75, we're going to use a lot of energy, even though the unit starts slower and ramps up. So there's no initial burst of energy like the lock rotor amps on a traditional system. But once it ramps up and cools the air off in the house, that unit is going to slow down at room temperature, and it's going to make minor adjustments that feed. And what it'll do is it draws the heat out of the furniture and the walls and the wood and the doors and the countertops as it's all releasing. Because of that second law of thermodynamics, heat is always going to cold. So we cool the air in the house, the heat is given off to it, and the unit makes small adjustments in doing that. Once everything in the house is the same temperature as the thermostat is calling for, so you now have your house at 75, you've reached this dynamic point of thermal equilibrium. So everything in the house is 75. My unit can go into its lowest mode and maintain 75 and then shut off. And then when it gets a little bit above 75 again, that unit's not going to have to make this large recuperation. So it's going to start off slow again. So if you keep your house at temperature, keep it tempered, it's going to use far less energy than turning it on and off all the time, like a single stage system does. And if you have an oversized single stage system because you need it to do what it needs to do on the hottest day of the year, so all the other days it's really too big, that thing's going to turn on and off all the time, which causes all kinds of comfort and energy problems. So putting in inverter technology and getting rid of that oversized single stage stuff, just like Alex said, is extremely critical if we want better operation of the grid overall.
Next question, could you provide some more info on the upcoming training that you mentioned? Registration link, date, time. I put a link into the chat with access to it's through the switches on, and it lists all of the training initiatives through Tech Clean California. We will be doing a training in October in Brea in Southern California, and then in December in Concord, up closer to the Bay Area. But we'll also be in the Sacramento area early next year in the winter time, probably January, February in Stockton and Elk Grove. So stay tuned for that. You can go through the link that I posted there. It does require you to be a tech enrolled contractor. But if you're not and you still want to attend, just send us an email. If there's a space in the class, we may be able to have you sit in the back.
Those classes are fun. We teach a lot of concepts that we can't get out in an hour and a half, and it's 3 days. It's fully immersive, it's fun, and you get a really good hit of building performance stuff. So it's a great learning experience.
Yeah, and I'll also point out that SMUD has a list of really great trainings. Megan posted a link to an upcoming training with Russ King on residential load calcs. So make sure you take advantage of all that great stuff. And if you have ideas for other trainings that you want, or you want a deeper dive into some of the subjects we covered today, just let them know. I'm sure they will be more than happy to assist.
Okay, very
Okay.
good.
I think we got through all the questions. The one I didn't comment on was Ahmad had some questions about ventilation and some of the approaches that we'll take. So we had discussed using a bath fan, exhaust only if the house is relatively loose, which is what we're looking at in most retrofit scenarios. But if it's really tight and we're doing, passive house standard or new construction or going down to the studs, approaching it with an HRV or ERV, some sort of balanced ventilation is always the best way to go. If you do that, you need to make it really easy and clear to the customer. They need to be educated on how to use that system. Otherwise, the filter will never get changed out, and they might end up turning it off, which could lead to health outcomes that we don't want. So we've seen those done poorly time and time again. So customer education really important.
Yeah, we've seen we've seen ERVs or HRVs installed in houses that were so loose they didn't need them. And then we've seen them installed in ways where the noise was so audible that the people sought out the switch to shut off the noise, not knowing what it was. And there's a big problem, like when that person that did that job sells that house, that new owner has no idea what that switch is or what that noise is or where that filter is. So my advice on any time you're putting in one of those things is it needs to be like put it in a laundry room on the wall or in the garage where it can be seen, and it needs to have the instructions like taped to it or on it, so that in any case people know what it is that's making noise, and that there needs to be maintenance on it. Over my career in home performance, I've seen dozens of them that were shut off or were never serviced and caused smells, and that they were just they're after the initial installation, nobody cared about them anymore. So it's really important that step gets done, or exactly like Alex said, if you need an ERV or an HRV in the house and somebody turns it off, there's going to be a negative effect. We like the ones that are just the bathroom fans that do the two-way, like the Panasonic HRVs are really cool because they're super easy and they turn on. But that's just my experience coming through on that.
Right. We've seen some practitioners put a big label next to the switch for it, for example, just so that there's a very clear reminder if anyone ever moves out, what it actually does and that it has an important function. Okay, I don't see any additional questions in there, so Megan, we'll hand it over to you.
Okay, great. Just a reminder that we'll send the presentation out after this. Thank you all for joining us today, and thank you, Alex and Larry, for your time today. This was really great as always. So we will see you again, and everyone else, check out smud.org/workshops for what's coming up. We've got a lot of cool stuff on the calendar for the fall. So everyone have a great and safe rest of your day, and thanks for joining us again. Bye, guys.
Thank you, guys. It was a pleasure, like always. Bye-bye.
Hi, everybody.